All right, welcome back, everyone. Our next speaker is Emma Brunskill from Stanford. She's helped us understand a lot of these sample complexity results for MDPs and things, and has also has a lot of practical impact herself. So please take it away.
Thanks. I'm so excited to be here. I've had the pleasure of seeing a number of you at different conferences this summer, so I tried to select a subset of things that I thought would have minimum coverage from what everyone's seen. I want to start with a question that came up a few years ago, which seems particularly appropriate being at University of Washington, which is, together with my colleague Zoran Popovic and some of our graduate students, we were interested in the following question. We were really interested in trying to help people learn things better, and Zoran and his team had developed Refraction, which is a game to teach people about plane fractions. And so you can see here that people learn to split laser beams in terms of certain fractions, and they have certain splitters. And the question that we wanted to look at in this case is, how do we keep people playing this game and persisting even though part of it might be difficult? And why might this be a reinforcement learning problem? Well, what we could do in this case is, depending on how the students were doing, or the learners were doing, we could change what they saw next. So as a really simple decision policy, you could think of something like just conditioning on the feature of how long they took to complete the previous level and giving them different next game levels according to that particular feature. But of course, there's a huge number of features that we could be capturing about how students are interacting with the game. And our particular question and opportunity was that we had about 11,000 students' data who had played this game with random levels. Now, overall, I think about 500,000 students have played this game, but we had a subset of it, which we did some random experimentation, because we were curious about what could help students persist for longer and how we could make that personalized and adaptive. And so our goal in this case was to learn a new decision policy to maximize student persistence. And it was then, so this was about 5 years ago, and this was my first start of thinking about how could we use old data to try to optimize future performance. So this is not the exploration problem. This is a case where we have a fixed amount of old data and we want to think about how we use it in the future. But I want to highlight that I think this falls into sort of a general legacy of thinking about reinforcement learning to amplify human potential and to benefit people in general. So while we're very familiar with sort of some of the amazing successes that are happening in the context of games and robotics, there's really been this parallel legacy of thinking about things like adaptive clinical trials, teaching machines. This is one from about the 1960s, and others where we could think about using AI and reinforcement learning to try to do personalized adaptive interfaces that are going to help people accomplish certain tasks. And I care about those applications a lot, and I also care about the technical challenges that they introduce. So if we think about how these are different than a lot of the existing sort of technical challenges that come up right now in some of the amazing successes we've seen, in the context of things like Go and in a lot of robots such as MuJoCo, we have a simulator of the domain. And we therefore either have a simulator or we have an enormous amount of data to train in that simulator. And we can always try out a new strategy. And while it can be important to do sample efficient learning in these cases, ultimately, it's okay if we fail to play Go well for literally trillions of games, as long as when we finally have the championship game, we can learn well. Now, in contrast, if we think about sort of interacting with people, we're working on it, but we still don't have a good simulator of human physiology, behavioral learning. And so we can't just run things sort of, with simulated human learners for millions of trials. And at the same time, if we want these systems just to be live, then that has impacts on real people. And so in the context of the educational systems I think about, I don't want to fail to teach 1 million people fractions before we learn a good strategy. So really in my lab, we've been thinking a lot about sort of techniques to minimize and understand what is the data that's needed in order to learn to make good decisions. And I think this is both sort of a foundational challenge in reinforcement learning, but it's also one that if we could figure this out, then we could just learn to make good decisions faster, and then we could benefit more people. So if we treat the number of people in the world as essentially a finite budget, if you need a lot of them to learn a good policy for the rest, then less people are benefiting. So that's why I think this is very an exciting thing to think about. And I'm going to tell you briefly about what I'm not going to tell you about much for the rest of the lecture, which is, of course, a key question in this is how do we do smart data gathering and do efficient exploration? And so a large amount of my lab's work over the last 5 years has also thought about this question, particularly trying to answer this question in the tabular setting. And I think at this point now, we've basically closed that question for episodic tabular MDPs. There's also been some great work by colleagues over at DeepMind, closing this for regret first, and now we've closed it for PAC. But I don't want to talk about that so much today. I want to talk more about this issue I raised earlier with the fractions case. And before I do that, I just want to make sure we're all on the same page in terms of notation. So I'm going to use S to denote state, just like John Tzitsiklis did, for those of you who saw his talk a few months ago. I'm going to use pi for policy. I'm going to use V for the value function indexed by pi if we're looking at a particular policy. And I'm going to think about there being a dynamics and reward. And of course, in general, we don't know the reward function or the dynamics model. And in general, I'm going to be considering stochastic functions as opposed to deterministic. And the question that I'm curious about today to talk about is, imagine we have a data set D of n trajectories. So someone has previously gathered this data with customers or with students or with patients. We may or may not know what pi b is. In the context of healthcare data, we often don't know what pi b is because that's actual physicians making decisions, and they don't normally write down their decision rules for us. But we have this access to this data set, and we want to think about how we can use it in order to make better decisions in the future. So this is a challenging problem for a number of reasons. The first is that it essentially involves counterfactuals, or what-if reasoning. So if we have a sequence of patients that are being treated with sequences of different trajectories of patient treatments or exams, et cetera, and then we have some sort of outcome about health outcomes, then the question we might want to ask is, when a new patient comes by, what should we do? And what's going to optimize their health outcome? And the challenge in this setting is that we have censored data because we can't actually see what would have happened if I had treated this particular girl with a different sequence of treatments. And of course, this issue arises even in the context of multi-arm bandits, but it becomes particularly challenging in the reinforcement learning case. So we have this censored data problem, and it gets worse and worse with sequential data. But I think the other thing that comes up particularly that's not as present in bandits is this need for generalization. Because if we think about making a sequence of decisions, and let's imagine for now we have a finite set of actions, then the combinatorics of the number of different possible sequences of actions grows up exponentially with the horizon. And yet we're not going to want to try exhaustively all different action sequences. And so we're going to need some way to do generalization. And that's typically going to require us to do some sort of parameterization of our policy or our models or our value functions. Now, I think it's a really exciting time to be thinking about this. There's, of course, been an enormous, wonderful literature about causality and causal inference. And then now there's been starting to be a lot of interest in combining this with machine learning. And to me, one of the reasons this is so exciting is because people in epidemiology and econometrics and biostatistics have been thinking about these issues for a long time, but from a very different perspective. And so I think it's a really exciting time to start combining between these insights so we can sort of unlock all of this observational data that we have access to now. Now, in the substantial literature, a lot of it has focused on the treatment effect estimation problem. The idea of saying we want to make a single decision, a one-time step, and decide between, say, a control and a treatment in particular. And we want to be able to estimate the effect size of doing that treatment compared to the control. But when we get into the reinforcement learning setting, we have this challenge of covariate shift. So in general, of course, different policies are going to take different actions and result in different state distributions. And I really like this, this figure that was in a Nature Medicine paper from some colleagues, David Sontag and Fernando Joshi-Velez's lab, which illustrates the challenge. Some of you might already be familiar with this, but I think it's a nice thing to go through. So let's imagine that we have a whole set of patients, and then we want to evaluate a particular decision policy. So we first say, well, our decision policy is going to do mechanical ventilation on these patients. And so then suddenly a whole bunch of the data that we have is excluded because those patients didn't get mechanical ventilation. We then say, well, what if those patients experience discomfort? Under our policy, we would apply sedation. And then again, a whole bunch of people did not get sedation, so we can't use their data. And you can repeat this over time steps. And so you can see that if you look at sort of a really large, maybe 100,000 patients, which is a reasonable number of patients, if you start to winnow out the number of them that happen to get the decision policy that you care about evaluating, then you can start to really shrink the cohort of people or the amount of data you have that matches. And so that becomes a really big challenge because as we have less data, we expect to either start to need biased estimators or high variance estimators to try to use this data to figure out what we should do for new patients.
But why do you think it's representative? It's even more worrisome.
What do you think? What?
The end thing that you got is a representative sample of what would have happened if you run your policy.
It's a great question. So why do I think this, even for these, 6 people that I have left, are they representative? It's a great question. We'll have to make some assumptions under whether or not we have certain features that can cover how we're going to generalize in terms of what features are describing the patient. And then another really important assumption we're going to have to make is that the variables that were used to make these decisions are available to our algorithm. So essentially that there's no confounding. That there aren't decisions being made. So for example, maybe somebody has one blue eye and one red eye, and that's totally critical to use to decide what your patient treatment is. If I don't have that in my notes, if my algorithm doesn't get access to that, that can lead to estimators that are wrong, essentially, because we're not having access to variables that we need to have in order to make good decisions.
So what I meant, let's say, take mechanical ventilation.
Yes.
So part of the people that didn't get it,
Yes.
your algorithm will say that you should give it to.
Maybe, depending on the value.
Right, depending on the value.
Yes.
But those, so this is what I'm really worried about.
You're worried about for these people that didn't get it?
Selection bias, right?
Exactly. So that's my point. So, well, there's 2 things. We're going to be in the potential outcomes framework for those of you that are familiar with that, and that's going to make, and we're going to have to make sequential potential outcomes framework assumptions, and we're going to assume that there's no confounding, so that we would have had all the variables we need to make that decision, and so then we are going to be able to extrapolate to what would have happened to those people who didn't get it if they were to, assuming we have access to all the variables. Yeah.
Just a clarification question for that. So you mean that at the time when the mechanical ventilation decision was made, it was made by some doctor, and the doctor was looking at some characteristics of the patient, and you have information that they were looking at exactly that same information, and your policy can be based on that, and that will be the assumption.
Yes, so we have access to all the covariates that were used by the doctor to make the decision. And while in some ways that seems like an incredibly strong assumption, at least in the US, we have a fairly strong legal culture around medicine, for better or worse. And what that means is that people have to do a lot of documentation. So I think that a lot of our electronic medical record systems right now don't have that information in easy form. But as we get better and better at NLP on those notes, I think it's not a crazy assumption compared to what I would have originally thought, which is this is always going to be impossible. I'll go back to this more later. I will say that one of the big things we're doing in my lab right now is to try to understand if there is confounding, what can we say? And can we get bounds on the resulting values, even if confounding is possible?
Specifically, when you say confounding, what do you mean? Do you mean a missing variable?
You know, missing variable that is used to make a treatment decision that we don't have access to. There's a lovely example of this. Some of you might have heard of it. Some people used to conjecture that smoking was not related to lung cancer, and there was another missing variable that caused you both to be more likely to smoke and have lung cancer. And they did this sort of a confounding analysis to show that in that case, the amount of sort of confounding that was going on would be enormous. So sometimes you can say, if you have a limited amount of confounding, it can't affect your estimate of the treatment effect that much. So this is why this is challenging. Okay.
Quick clarification. So are you starting with a set of homogeneous patients? Are you starting with a set of homogeneous patients?
Good question. No, we don't have to be. So this is, we don't have to assume that we have a complete coverage over the state space, but that's going to restrict, we're not going to be able to make assumptions for initial states we don't have.
So when you start at like deciding who would take the mechanical ventilation, is that like you're thinking, because their patient's characteristics are not the same, so how?
Right. So we would have access to all those variables, and in fact, some of you might have seen the recent DeepMind paper that was talking about. I forget actually what the medical condition was, but it was mostly over males, and so they can make assumptions that are saying like for males, this is how well this policy would do, or this, these are how well our predictions would do for males, but they can't generalize to females well because they don't have very much data, and they can talk about how well they do in that case.
Deep learning was just going to generalize and solve it.
That is the goal. Not sure everyone carefully said. So, okay. So this is the general thing that I would like to be able to solve. I would like to say we want to pick the policy, or we want to do counterfactual policy optimization, which is I want to take my data and I want to figure out what we should do in the future. And let's say we want to do something like the following, which is we have a set of hypothesis classes, and I'll talk in a second about what those might be. We want to figure out the best policy in the best hypothesis class that has the best performance in the future. So here I'm looking at an estimate of the value of that policy in the future. And you might think this is a reasonable thing to do. We're sort of just getting a good estimate, and then we're taking the best of those, whichever policy has the best estimated performance in the future. Unfortunately, that's not sufficient. So my student Shayan Daroudi and I and my former postdoc Phil Thomas showed a few years ago that you can't just do this. And as often I find in science, the answer is obvious in retrospect. So why is this true? Well, this is just an estimator of the value, and different estimators will have different amounts of bias and variance trade-off. In this case, we were looking all at unbiased estimators, but some of them have very high variance, some of them have very low variance. And if you're taking a max over estimators with different amounts of variance, you might make systematically bad decisions. So we can't just look at sort of what our estimator says. We're going to need some notion of the quality of those estimates. And so that's what's really led me into, at my lab, kind of into this journey of a quest for sort of, batch policy optimization with generalization bounds. And when I talk to my colleagues who are in supervised learning, they always look at me sort of quizzically, because they're like, we have that, it's called structural risk minimization. Or they say, we have empirical tools for that, it's called cross-validation. And I said, yes, I know about both of those things, but in RL it's harder for a number of reasons. And I just don't think we have these yet. I think we're making steps. And I think if we could do it, there'd be so many application areas that we could do a much better job at. So what would I like us to do? I'd like us to say, I want to figure out a policy that basically has the best bound on how well it's going to do in the future when I deploy it. So I don't really care about how well my policy does on my training set or my existing data set. I want to know if I deploy it in the future, on average, how well is it going to do for students or patients or customers? Yeah.
Just wondering about whether, you really insist on that we should have a sequence of hypothesis basis, or should you just have a bound that the deviation bound and the interval lengths will depend on the policy and how it interacts with the data, right? It seems that you have this additional structure.
You mean here,
yeah.
In this case?
Yeah.
I'm putting this in here so we can also take into account model selection. So that we can think of you to also say, do I want to use a linear policy class versus a deep neural network policy class, and which of them, so I can trade off between them.
Those are, artificial boundaries that you may not need actually, because you should be comparing policies to policies, and how certain you are about your estimate of the value of the policies.
The reason why I would like to think about it in that case, I think it's a good start. The reason why I've started thinking about it more in this case is that I think the bounds that we have right now tend to ignore any structure in the policy class or value function that we have. And in structural risk minimization, we take advantage of that to get us generalization bounds. And I would like to do the same. I'd like to say, I don't want to make assumptions about whether my world really is linear. I just want to say if I make an assumption that it's linear, this is how well you're going to do in the future. And right now, we have to make assumptions like the world really is linear, and I don't want to do that. So we can think of this as involving three different things: policy optimization, policy evaluation, and error bounds. And I think the part, I guess I'll first just say, I think it's already different than structural risk minimization because it's not clear even which sort of hypothesis classes we're talking about. So when we think about hypothesis classes, we could think about there being models, like dynamics and reward models is what I mean by that, or value function approximations, like deep neural networks or linear value functions, or policy classes. And so it's already, we have a lot of different choices of even how to represent decision problems compared to a lot of supervised learning problems. So we've done a lot of work on policy evaluation. What I want to talk about today is policy optimization. And I think the real challenge here is having good error bound analysis so that we can do policy optimization, we can do policy gradient, we can do lots of different things. The question is, how is it going to converge? Are we going to do well? Do we have any sense of how well it's going to generalize in our future data? And I'm going to argue that I think the existing error bounds have a lot of limitations, including work that we've done. So importance sampling bounds are possible for these cases, but they tend to completely ignore the hypothesis class structure. And so generally they're very loose. It just means we need a lot of data. And so in some cases that's very reasonable, like Phil Thomas had done work with Adobe. If you have millions of records, I think this is totally reasonable. When I look at some of the mobile health applications we're curious about right now, I think we're gonna have on the order of hundreds or thousands. So I don't think these are gonna scale. Things like if we make certain assumptions over our hypothesis classes, like kernel functions or averagers, we can get this type of bound, but we typically need a number of samples that's exponential in the input state dimension. And if we want to be able to capture all the covariates that describe patients or customers or students, I think that's not going to be feasible. And I think fitted Q iteration is really interesting to me for a number of reasons. One is that it's been around for a long time for batch reinforcement learning, but also it's sort of in some ways the foundation of deep Q learning. And so if we could better understand that, it's going to give us insights into deep reinforcement learning. The challenge I see is that a lot of these bounds require pretty strong assumptions about realizability or bounds on the inherent Bellman error. And in particular, the bounds that I'm aware with, and maybe somebody will know of additional ones to point me to, mean that if we're not realizable, we're going to have bounds that depend on unknowable quantities, like the inherent Bellman error of a function approximator in a particular domain. And the problem with that is that's going to prevent us from doing model selection. Because if we have a linear class versus a deep neural network and we can't evaluate those bounds, I'm not so concerned necessarily about exactly what those values are, but I want to be able to compare them. And so I think that's one challenge with these type of analyses so far. And then there's also been some really interesting new primal dual approaches that are really promising, but they typically have similar dependencies. So I think this is really hard. I think it's a really exciting direction. I think there's a lot to be done. I'm going to move the goalpost. Oh yeah, Alec.
So we have structural risk minimization in theory with using the uniform convergence bounds, however refined we want to make them. But I feel like it in reality it only works because we can do it with cross validation, right? And that's going to be a much better behaved estimate. Do you really think if we didn't have cross validation, structural risk minimization was going to work in supervised learning?
I think it's a great question. I think it might have still been useful for model selection. So I'm not sure it's going to tell us whether this is good enough for us to deploy or not, because the bounds would be so loose. But I think it might allow us to still say, do you want to use linear or do you want to use quadratic? Maybe. It's tricky about how loose those are. But I also would absolutely argue that we want cross-validation for this scenario too. Yeah.
Isn't there a problem or two problems with cross-validation in this domain? So one of the problems is that you still have the off-policy issue. You still have to have the variance issue that you have to control. If you need to do a selection at the end of cross-validation, you need to know the deviation bounds for cross-validation.
Well, I'm not saying that cross-validation is going to work here. I'm saying that
yes.
This is not necessarily a viable alternative in my mind.
Well, it seems to me that cross-validation is calling for the same type of analysis if you take it seriously, and if you're worried about that you might be overfitting to the noise, and in these settings, you're very prone to overfitting to noise. In cross-validation, you also need to make sure that your algorithms are stable. If they're not stable, and no one knows, for example, if you use neural networks, whether they're going to be stable the way people use them, right? It's kind of like, yeah, it's in practice, people will continue to use it, but it's actually working or not, that's a good question.
No, I guess I'm saying that I'm using these as high-level inspirations. I don't think we're where we want to be for either of those. I guess I'm using cross-validation as a loose way to denote we would like an empirical way to do this. I don't think this is an empirical way, to Alec's point. And I think we'd also like theory. And I don't think we've got either at this point. OK, so this is hard. Let's see if we can do something easier. And let's see if we can do the easier thing, and then we can hopefully go back to the harder thing. So an easier thing to do is to find a good in-class policy, given the past data. And not necessarily have any bounds on future performance. Just say we're going to try to find something that seems to be good within a parameterized policy class. And while that seems like I've just made it much, much, much easier, which I sort of have, I think that it's not totally unreasonable. And I'm going to argue later that for interpretability reasons, this might be a nice place to put in some human knowledge. So I think there's good reasons to think, at least in some of the applications I consider, that having policy parameterizations might be a useful place to put in interpretability knowledge and get benefits. Okay, so can we do this? So to be specific clear, what I want to do right now is I'm going to do some form of policy search or policy gradient, but I want to do it only with batch data. So a lot of the methods right now that are considered off policy gradient still actually are gathering new data in the environment. I'm going to be restricted to saying I've only got the medical records that I have or the data that I have. Okay. So one of the reasons we were curious about this is that I think policy gradient methods are enormous, as you were just hearing from Emo, and I think many others are familiar with it. If we look at, but there hasn't been that much work on the batch data setting. And I also think that one of the other reasons why I care about this is that I always find it kind of frustrating that in the vanilla policy gradient algorithms, we just talk about throwing away all the old data from the previous iteration, which seems insanely wasteful. And in sample, in cases where those samples are people or other high stakes scenarios, it seems like surely we can do better. Now, people have certainly tried. The problem is that if your policies are quite different over time, the variance you introduce can be too large, and so you might not get a benefit. So if we look at the policy gradient theorem, we can think of it as the following, where we have sort of, we think of the value of a policy as being the sort of integral over the value of each state times the stationary distribution over states under that policy. Now, if we think about sort of expanding these out and thinking about what we get in these different scenarios, then sorry, I have more animations here than I expected. Then if we want to use this for a different policy, then we're going to have some challenges. If our data was gathered, let's say, under a behavior policy mu, and now we want to evaluate the value under a different policy, the problem is that sort of our distribution, that d pi, our stationary distribution over states, is going to change because our policy is different. And so one of the previous algorithms for trying to look at this said we're not going to deal with that aspect of sort of the covariate shift. Our covariate shift is both going to change the actions we take and the states we reach. So in this nice paper by Degree and all, they looked at sort of, well, what if we keep looking at just sort of the stationary distribution under our original behavior policy, the policy we use to gather our data, but we're going to account for sort of the difference in the actions we take on top of that. And this had some nice empirical performance. You can now use it offline. The problem is that you're going to get a bias of your gradient estimates, because you're not really, this isn't really the value function you're going to get when you deploy, because you're generally going to reach different states. And in fact, if you don't reach any different states or take any different actions, it's going to be exactly the same. So what we would like to do in this case is to think about, well, what would we do if we wanted to actually correct for this? Well, we could think about sort of using an importance sampling technique to reweight our data so it looks like it's from the distribution of the new policy that we want to evaluate. The problem is that if we do this in sort of a naive way, and I'll expand this in a second, we're going to get a really high variance estimator. And I think to see this, it's useful to think back about sort of the standard importance sampling for reinforcement learning. So in importance sampling in general, if we think of the value as being sort of what's an average over the probability of a trajectory, so I'm denoting that with tau, times the reward of a trajectory. So the beautiful thing about importance sampling is that if we have data from a different distribution, from a different policy pi b, then we can just reweigh it, so we can leverage our data from our behavior policy pi b, and then we have this ratio. And because the dynamics is the same in both environments, then we just get this ratio that depends on the actions. I know everybody here knows that, but I just want to contrast that in a second. So that's been the first time I'm aware of people doing that for RL, is sort of doing a Precups paper from 2000, but there's been lots of extensions and continues to be, including from my group and others, to think about the variance in these estimates and things like that. I think one really nice direction that's happened in the, yeah, sorry.
Okay. Emma, what are you mentioning about the batch data you have in the past? Like, are there states that is it that every state you've seen in the past has every action played in the past?
Yeah. So we're going to have to make an assumption to get, we're going to make an assumption. So Daniel's question is, what assumption am I making about the coverage of the behavior policy? And I'm going to make an assumption that the behavior policy is going to cover one of the optimal policies. So it doesn't have to be all of them, but it has to cover one of the optimal policies that I'm going to construct. Well, I'll say in a second, and then you can tell me if it answered your question. So in this case, we see this ratio. Oh yeah, sure.
It's also related to Dan's question. So when you have these behavioral policies, you have the data that's collected, but when you're doing blend sampling, you need to know the ratio. So are you thinking about some propensity score here, or how do you get?
Yes, great question. So you mean how do I get these?
Yeah.
Yeah. So in some of the work, we assume it's given, like that we have an algorithm, and like in our fractions example, we knew what it was. In that case, it was random. In other cases, we're going to estimate it from data, and under certain assumptions of asymptotic consistency, it'll be fine.
So like these healthcare settings, you're estimating it.
We're estimating
These numbers are
from data. So we have a set of covariates, and we estimate the probability of the action from those. And we're going to need assumptions of coverage, almost always, that the policy that well, we can either assume that this is going to cover everything that we want to evaluate, or if you're making assumptions that your rewards are all 0 or above, then this may just give you a lower bound on the value function if you don't have coverage. And so that can still be okay for optimization. So the nice thing so this is generally bad because this is going to depend on the horizon, and I'm sure other people too, have proved that this variance of this estimator can generally be exponential in the horizon, and so that's horrible, which is why I think nobody uses this in practice for long sequential problems. But one really nice insight that was made, as far as I can tell, kind of in tandem with 3 groups over the last couple of years, is just to say, well, this particular way of writing down the value function in terms of a probability of a whole trajectory times the reward of the trajectory is not the only way to do it. And the other way is this way that looks very similar to sort of the policy gradient theorem I was saying before, which is what is the stationary distribution over states and actions under this policy times the reward of that state and action. And just to be careful here, d pi here is now going to incorporate the discount factor. So it incorporates sort of the weighted sum of discount that you're going to be in the state and action. And the nice thing is that when we write this down here, then we can play the same importance sampling trick, which says instead of having to think about this product, we just think about what is the ratio of how much time we'd spend in that state and action under the new policy divided by the old policy. And now we've got rid of this sort of horizon issue. So that, I think, is really elegant, and people showed that you could use this and get much better empirical estimates for policy estimation. And so a really natural, yeah?
How is this a function of S0?
How is this a function of S0? Because d pi of SA is assuming you're starting in S0, and it's going to have a discount factor.
And what is cap J?
And what is what?
1 over J at the last equation.
Here's our number of data points. Yeah, so we're going to do an empirical average, like from our existing data set. So this was all for the policy evaluation case. Generally, there were some experiments here that were not, but generally this was all for the policy evaluation case. So our insight was quite a reasonable one. This is also with Alec and led by Yalu, and also with Adit Sawatram, that we could use this for policy gradient. So now we're going to take our policy gradient theorem, and we're going to use this ratio of stationary importance sampling in order to get a true unbiased estimator of the gradient. And so now we're correcting for the state action distribution. And we're going to use the approaches that I mentioned on the previous page to try to estimate this from data. Yeah?
So if those estimates are biased, is this going to be bad for us because the gradient is going to be biased this time? So how are we going to deal with that?
Yes, so our bounds are going to end up, the question Chava said was, well, what if those gradient estimates are bad or biased? Isn't that going to be a problem? Yes, we're going to be able to have a theorem that depends on these being close but not perfect. Yeah.
Also, how do you get the? I mean, this looks like a little bit of an odd way to write it because with the Q pi, you'd also have to do the same trick.
We do. Yeah, so we end up having with, Sean's question is like, well, what about Q pi in this case? We're going to do an actor-critic style algorithm, and we're going to both use, we're going to use the batch data for both parts. So we're going to have the batch data to estimate the Q pi right now and do off-policy evaluation for Q pi. And then we're also going to use the data to get a ratio of the current policy. And so it's going to look very much like a policy gradient algorithm, but we're always using the same data. And so we're going to have a current target policy. We're going to estimate this, take a step, and repeat. And in particular, this is the algorithm. So we're going to start off with the behavior policy, just warm start. And then from 0 to t, this is all, again, just computation. This is no new data. We're going to sample some of our old data to estimate W. W is our ratio of the stationary importance sampling. And then we update our critic, and we take a step. And one of the things I want to mention there is, so we have some assumptions under which this, to show that this might be a sound thing to do. So we need to have some assumptions that we saw before over whether or not the policy, the stationary policy over actions and states, if that's 0, that we also in our target policy are 0. So this is basically a coverage assumption. And one of the things we do is we construct this sort of augmented MDP, where we think about if you were going to go outside, so your data is going to cover sort of a set of states and actions. And what we're going to say is that if you go outside of that set of state and actions with your policy, we're going to define the reward there to be 0. And so that's basically just going to give us a lower bound over any policy that exits kind of your envelope of state and actions that we visit under mu. And that's going to be OK in the sense that if we make okay, so what we're gonna make an assumption here is that there's gonna be at least one policy that's optimal that is covered, and then that means that that policy is not gonna go out or is gonna have a value that's at least as good as is in the original MDP. So our pi star is still gonna be optimal, but everything else is gonna either have the same value as it would before or a lower bound. And so this led us to my knowledge, the first proof of convergence to a local optima for a batch policy gradient. We need a few other additional assumptions. Most of these are pretty common. And I think one of the interesting things about this is that we don't have to have all of the policy. We don't have to be able to cover all the policies you're going to go along your gradient updates, only the optimal. So a lot of like FQI style bounds require you to, all of the policies that you evaluate have to be within your space, and you have to be able to evaluate them accurately. We're not going to have that here. Okay. So this is only to a local optima? Yeah.
So even if the optimal policy is not covered, you could still like improve over the previous policy, right? Like it's
probably. So the question is, you know, if an optimal policy is not in there, can you still improve? Probably, but we're not making guarantees in that case. It would depend whether if one of the policies that is covered is better. So one of the nice things about this is I think it's always nice if there's theory as well as useful benefits empirically. And so we did some empirical experiments to see, well, how much lift does this really give you? And so in the context of something like carpool, this is the behavior policy. So this is like how well your behavioral policy would do in the environment. And if we look at something like off-pack, which is the one that does not correct for the state distribution, but just the actions, it can do a lot better. It can learn, so this learns a policy that's much better than the original behavior policy. But you can see that our approach does substantially better, and in fact basically learns the optimal policy for this domain. And so the nice thing about this is just really saying we're going to be able to do just much better with the same data. It's exactly the same data. We're just doing a smarter policy gradient algorithm, and by correcting for the state distribution, then we're going to end up with a much better policy. It was a little hard to compare to other algorithms because most of them are not looking at the batch setting, but we looked at a couple other ones that are sort of state of the art and adapted them to this case, and these ones don't tend to be able to do as well in this scenario. Sean?
What was the off policy? What was the behavioral policy?
This was the behavior policy, and in this case, I'd have to look back. I suspect it's a combination of optimal and random.
This one was uniform.
This is uniform.
So how would the uniform
random
ever get to the
standard?
Yeah, this is pretty easy. Yeah, this is a.
Okay.
Yeah, so this is not like a sparse reward problem, or it's not. It is sparse, but it's pretty easy to get it under the uniform policy.
Different. Okay.
Yeah. This is not. Yeah.
Sorry, how much data?
Good question. I think in this case, do you remember? I don't. I'd have to go back to the paper. I don't think it's enormous. I don't know, 1,000 trajectories, 10,000 trajectories. It wasn't millions. Like it was. Yeah.
Certainly no more than 10,000.
I don't think more than 10K, but I'm happy to look it up. So the second case that I think is interesting, and this maybe goes to Sham's point, is so this is a case where under your behavior policy might not be very good, but it would actually encounter good rewards quite a lot still. We looked at an HIV treatment simulator where that is not the case, where it's much more like a chain domain where you have to take the right series. So something more exploratory or more random is going to do very badly. In this case, you can see the behavior policy is here. In this scenario, we can, again, we're not going to get to optimal, but we're going to get to much better. And so this goes to the question of before. So in this case, I don't think that the optimal policy is covered, but we can get a substantially better policy than what we see before. And again, this is just with the same data. And so I think that the interesting thing about this is certainly something you can imagine embedding within like an online algorithm too. And this hopefully should just allow us to have bigger steps, right? We can just do more with the same amount of data we have, and so we shouldn't have to collect as much data because each time we can do bigger jumps. So just to summarize that part, and I'll jump to here, this is the first convergence result as far as I know to non-tabular off-policy policy gradient, and in simulation it seems to work pretty well. And so that gives us this, where we can guarantee we get to sort of a local optima. But this is pretty far from the original goal that I was saying that I wanted to get to, and so let's see if we can do a little bit better. So another is that, okay, let's still stay in the in-class policy, but let's not just guarantee we get to some local optima, let's try to guarantee that we get to the best thing in class. So an oracle might say this is the best policy in your policy class, and I want to compare to what is the policy that I select, and I'd like to be able to have some sort of bounds which scale with the complexity of my policy class and the amount of data I have. And so asymptotically, I want to be able to get to the best policy of my policy class at sort of, a square 1 over square root n rate. And to my knowledge, we're the first group to do this. This is led by Xinquan Ni and also with a great collaborator, Stefan Wager. And this has been really fun for me because they're sort of statisticians and econometrics people, and it's been great to learn about some of those techniques. We can't do this for all types of policy class, but we can do this for what we call when to treat policies. And so this is something like the following, which is, what would be a personalized policy for when to take the ventilator off? Or it doesn't just have to be a single decision when you stop. It can be you decide to start HIV treatment, and which HIV treatment do you start? So you decide you have an ongoing process, and at some point you make a decision, and it can be one of a set of A decisions. And we want to be able to account for lots of different things in this case, including that we're not going to assume that we know what the behavior policy is. So we can leverage, we're very interested in this for healthcare data. And you can think of, as an example of this, could be linear threshold policies, but that's not the only ones we can handle. So something like as your CD4 count goes down, then if it drops below this, and you're in a certain range of how long you've had this, then you start HIV treatment. That would be one example of the linear threshold policy. Or another case where as a function of time step and a health metric, you switch from treatment on to treatment off. And this is where I think this can, the structure we can put in the policies can be very helpful, because these are things that I could imagine visualizing with doctors and saying like, look, this is what our policy is doing. Do you think that's reasonable? Do you not think that's reasonable? And it can be a nice place to make things a little bit more interpretable. So I know I don't have a lot of time, so I'll sort of flash some of this stuff up. One of the things we were interested in doing in this case is try to have things where we could do, we were really focused on policy optimization, not just policy evaluation. And we wanted to do so in a way where we could be robust to some aspects of how well we can model the probability that people took certain actions, because we're just estimating that from data, and how well, if we're building sort of Q values, how good those are. So let me just step through that and just so I can show kind of the idea. So the idea in this case, and it builds off of Sham's work and Susan Murphy's work, is to think about an advantage decomposition. So we could think about in this case, because I have particular structured policies, of what is the value of stopping now and treating in a particular way versus what is the benefit if I wait one more time step and then treat in that same way. So what is sort of that relative advantage? And if we think about that, we can write down sort of the difference between our particular value of our policy versus a policy that never treats as a series of these advantage functions. And this is a decomposition that both Susan Murphy and Shyam Kakade have proposed before, and we're going to use it in the off-policy setting. Yes, I'll wrap it in like zero. And so the reason this is interesting is that this thing on the second-hand side is going to sort of be something we can think of as even like a single time step case. And that's going to allow us to leverage, let me just quickly put this up because The reason I think this is interesting is this is really leveraging some econometric techniques and semi-parametrics, which is something that are new to me but is exciting to learn about. I think that the reason that these are intriguing is because we're going to treat a whole bunch of variables as nuisance parameters. So like we don't really care about what is the probability that the physician decided to treat or not. We just want to use that information to help us understand whether this policy is better. And similarly, like we don't really care about what those mu's are. We just care about whether or not this policy is better. And so we can treat these nuisance parameters and learn them less well than our main target and still have these sort of 1 over square root n rates. And again, just to sort of highlight where I see different communities coming in, Dylan Foster from MIT just got Best Paper at Colt this year for looking at similar stuff for sort of this orthogonality or nuisance parameters in the context of machine learning. So I see sort of there's a lot of interest in bringing this over to control decisions that we might be thinking about in the sequential setting. And so this result, sort of this decomposition, allows us to get these sort of regret rates. I'll just say briefly so I can wind up. We compare to things like fitted Q iteration. As you might expect, if you have very small amounts of data, this is the amount of data we have, fitted Q iteration is generally going to do pretty well because you have a parametric bias. But as you get more and more data, it can be stuck. It's not necessarily asymptotically consistent. Whereas if you look at different domains that we have, green is us, as you get more and more data, you're going to be asymptotically consistent and we'll have better regret rates. And I think in terms of the policies that we get, if you look at sort of fitted Q iteration, it doesn't have this structured policy class. So you can kind of have this weird behavior where the policy it learns, it's sort of like, well, wait, if I'm slightly above, minus 2.3, but a little bit less than 0, I suddenly switch whether I turn on my policy or not, and then I go back. Like if I was a doctor, I'd look at that and be like, well, that's sort of weird. Like, is that just a bug? Is that sensitivity? Like, why is that a reasonable policy? Whereas the one on the left, because we've imposed that structure, kind of has this clean, this is where we'd make the decision, is that boundary in the right place? So just to wrap up, I think that there's a huge amount to be done in this quest. I think if we could solve it, we would sort of be able to unlock a huge amount of the observational health records that we have out there. It's not, of course, just my group. There's been a lot of other really amazing work. And I think one thing I just want to highlight there is that I sort of thought this problem was a big thing for maybe education and healthcare, but maybe not so much in sort of, like e-commerce. But I was talking to some colleagues who said, oh no, like actually even for things like, Amazon and Netflix, if you deploy an intervention, it might be that someone's, maybe Chrome browser's spam filter systematically reroutes this, So often you're going to have confounding or challenges or that mean that a lot of these questions are going to come up in many different types of domains, even beyond the ones that I thought about initially. So just to close, it's clearly a really hard problem. I just want to highlight that I think that there's room for optimism. So if we go back to this example I said at the beginning, we were trying to learn a policy that increases student persistence. In this case, we had the advantage that for better or worse, students drop out fairly quickly. So our horizon is fairly short. And so in this case, we could use importance sampling techniques to get a good estimate and predict that when we were going to deploy it, we would increase student persistence by 30%. And so when we did a new experiment, we found that indeed we learned a policy that increased student persistence by 30%. So I think that's a good highlight for why it is the fact that both these methods really can get estimators that allow us to predict future performance in a reliable way, and that in many cases there's a huge amount of room for optimization beyond what we can do right now. Thanks.
Time for a question.
So you started by saying that generalization is complicated and you don't know anything. At the end of your talk, did you come up with something that looks like automated generalization method, would you say, or generalization is still?
Yeah, I don't know if I said you can never generalize, but I did say it was hard. I think in this case, for like the when to treat policies, we can do generalization. We have something that's a function of how complicated your policy class is. Like this is kind of what our result looks like. It's something that says, if you have a policy class and this is how complicated it is, like as a function of k pi, this is what your regret will be like. So I think we sort of have the structural risk minimization for this type of problem. A lot of problems are not when to treat policies, and so we'd like to be able to extend this to the more general case. But I think at least this is a start towards those type of guarantees.
seen applications like this in infectious disease or infectious disease?
In infectious disease, great question. I have not. There might be in epidemiology. One of the challenges I think about working across discipline is we all use totally different notation, and they tend to call things dynamic treatment regimes. My impression is that I haven't seen a lot of this in infectious diseases, but there certainly might be for modeling. My guess there's a lot of additional complications. So another thing that I'm assuming in this case is that you have independence of treatment. So like if I treat one person, that's not going to have spillover effects. But in like whether it's Uber or infectious diseases, like those you'll have crosstalk. And so I think that's another case where.
That's an important assumption here.
Yes. So there's the confounding issue that we talked about, but then there's also this independence of treatment. And I think in a lot of network problems, you can't assume that. So it's another really interesting direction.
All right, thank you.